In R2, it's convenient to use polar coordinates to describe regions with circular symmetry. You can use basic right-angle trigonometry to come up with relationships between x and y and the polar coordinates r and theta. We want to work with problems in R3. So how can we generalize polar coordinates? It turns out that there are two ways by which we can do this, and in this set of videos, we're going to talk about the first way. This first generalization is called cylindrical coordinates. Now, in cylindrical coordinates, we simply take the r and the theta that we defined in polar coordinates and extend it by adding a third coordinate, which is just the z variable. Visually, we have our three-dimensional axes, and like we said, theta is the angle relative to the x-axis, r is this diagonal element, and what we're going to do now is simply extend this vertically. The coordinates of this point here would be given as r, theta, and z is this vertical direction as it is in Cartesian. This point down here would simply be at r, theta, and 0. We keep r and theta as in polar, and then we simply add a vertical z coordinate just like in Cartesian. And because of all of this, we will have the existing relationships that we had before. X will be r cos theta, y will be r sine theta, and z will be z. So this is if you would like to go from cylindrical to Cartesian coordinates because you know r, theta, and z. And similarly, we'll have r squared is x squared plus y squared. And just like with polar, we're going to define r to be greater than or equal to 0. Tangent theta will be y over x. And of course, z will be z. So this will give us the switch from Cartesian coordinates into cylindrical coordinates. Now, as a basic example, let's take this point given in Cartesian coordinates as 3, 3, and -2, and convert this into cylindrical coordinates. So this means that x is 3, y is 3, z is -2. We'll have square root of 3 squared plus 3 squared, which is the root of 18, which is 3 root 2. We'll also have that the tangent of theta is 3 over 3, which is 1. Now, of course, there are multiple answers to trig equations like this, but when we have x is 3 and y is 3, this corresponds to a point in the first quadrant in polar coordinates. We are going to take the angle here to be pi over 4. So the point in cylindrical coordinates is going to end up being 3 root 2, pi over 4, and -2. The z value stays the same. Now, you always have to remember the coordinates given here are not unique when using something based on polar. The angle pi over 4 will satisfy the equation, but so will any 2n pi multiple of this. So for example, we could have the tangent of 9 pi over 4 also producing 1. So another acceptable set of coordinates would have been the following. Now, as another example, let's graph this point in cylindrical coordinates, 5 pi over 6 and 6, and then let's convert it to Cartesian coordinates. Now remember here that the first value is the radius, there's our angle, and there's our z value. So we'll take our standard coordinate system as we usually do. We'll have our angle relative to the x-axis, so there's theta, and this distance here is going to be 5 units. And in cylindrical coordinates, all we need to do then is extend the point upward. So this here would be 6 units. If we want to convert this into Cartesian coordinates, x is r times the cosine of theta, 5 times root 3 over 2. Y would be r times the sine of theta, which would then produce 5 times a half. And z would simply be the value given. So this point here could be 5 root 3 over 2, 5 over 2, and 6. Unlike cylindrical coordinates, the coordinates in Cartesian are unique. We don't have this ambiguity as we do with polar coordinates. Now, in polar coordinates, we have something called coordinate curves. And you can think of these as the basic building blocks of describing curves in this system. So in a coordinate curve, you hold one of the variables fixed, and then the other variable is free. For example, r is constant and theta is free. What that produces in R2 is a circle because your radius must always be at this fixed value, but the angle could be whatever it wants. If you fix your angle constant, then your radius will be free here. remember that we were always going to be using a positive radius. If we extend this idea to cylindrical coordinates, we no longer have coordinate curves because we are in R3. And what we then end up with is coordinate surfaces. Now, coordinate surfaces means one of the variables is fixed and then the others are free. For example, if we take the radius to be fixed and the angle and the vertical height to be free, what we find is the basis for the name cylindrical coordinates. This will produce a circular cylinder that has a radius of c, but the angle is free, so you can rotate anywhere from 0 to 2 pi, and the z height is free, so this cylinder extends to infinity. If you keep your angle fixed, your radius and your vertical height are free. Remember that this radius is always greater than or equal to 0. So if we take a look once again at our coordinate axes, what we will find is that this will be fixed, but now this is free to go up as far as we choose vertically up and down, and it's also free to go out far as we'd like in the radial direction. So what this generates is a plane. And finally, if z is fixed, r and theta are free, this will be a horizontal plane that extends in all directions because their angle is free to go from 0 to 2 pi, and the radial value is free to go from 0 to infinity.